In the first section here, 1.1, we're going to talk about, we're going to remind ourselves about how to solve linear equations, sort of go back into our brain and think about how we solved linear equations in past courses, and then very quickly transition that into how we're going to think about solving them in linear algebra. So we've already sort of defined what a linear equation is in the last video, but just to sort of say it more generally, a linear equation in variables x1 through xn is an equation that can be written of the form this. Right, so we've got, as a reminder, all the x's have powers of 1, which makes it linear. And then in this equation, the a's and the b's are real or complex numbers. Right, so the a's and the b's are either real or complex. Usually in our class they're going to be real numbers, but if you sort of get into higher mathematics, they could potentially be complex numbers, but not something we need to worry about here. N is just a positive integer. It just tells us how many variables we have, right? As we mentioned last time, a system of linear equations is a bunch of linear equations, so a bunch of equations that all have variables of power 1 involving the same variables. And so the key thing so like for example, this is a system of 2 linear equations and 2 variables. Now when we write a system down like this, what that implies is that the solutions are shared between the two equations. For example, whatever you plug in for x1, x2 here that give you -1, they also need to be able to be plugged in here to give you 3. Right? So the key thing that a system has is they share the same solutions. Sometimes there's 1, we'll see. Sometimes there's more than 1. And so I will put an S in parentheses there. And so what we're going to do on this page, you'll see that this equation, this system here is rewritten 3 times on this page. Actually, I'm sorry, it's rewritten 2 times. I'm sorry, I totally forgot what was going on here. This almost the same equation system is written 3 times. There are differences in the 3 systems on this page. I know they look very similar, and actually just tricked myself for a second. But like this one is different than this one because there's a 3 here and there's a 2 there, right? This one is different because there's a 2 here, and there's also the numbers here are different. So they're similar systems, but they are actually different, and they're different because I want to highlight different things that could happen. So this again is one of your chances to think about how we solve things, right? So I'm going to pause the video, or I suggest you pause the video and just sort of try to think about from past classes, what are options we can use to solve linear systems? And just to give you a hint, there are 3 of them. So maybe just take one moment, pause the video, sort of think about if you were given a system of equations, how do you go about solving that? Well, there are 3 potential options, or at least 3 options, obviously, since we'll look at 3 examples here. One option that people often like to go to is you can solve for one variable, like you could add the 2x2 to the other side, you get an expression for x1, and then you could plug that into this x1 and then solve for x2. And then once you have x2, you can plug it back in and get x1. So that's called back substitution. And the way I would describe that is you solve for one variable. Try to leave space here, obviously, because we're going to need the rest of the page to do these examples. So you solve for one variable and you sub it into the other equations. That's kind of easy to do when you have two equations and 2 variables, but when you have a whole bunch of equations or a whole bunch of variables, it becomes really, really cumbersome to do that. So it's not recommended for most systems. That's called back substitution, though. Another thing that we can do to solve linear systems like this from past classes is you could multiply one of the equations by something and then add it to the other one to cancel out a variable, right? And so you can add or subtract multiples of one equation to cancel a variable in another. And so we'll do that on one of these as well. The third sort of thing that I think about when when we're solving these things, which doesn't get taught a whole lot, but it's a very practical thing to do if you have computational tools like computers or graphing calculators, is you can graph them. Right? You can graph linear systems, especially if they're 3 or less variables. So you can graph the lines, and you can look for the intersection. And so we'll do that on one as well. And so these are sort of 3 options, and what we'll see when we do these 3 options, we're going to do one on each one of these problems, is we'll see 3 potential solutions, types of solutions emerge. So on this first one, I'm going to go ahead and graph this one. Now it's kind of tricky sometimes to graph, these are 2 straight lines, right? You can think about them as y equals mx plus b, but they're not really written as y equals mx plus b right now. So the first thing I'm going to do is I'm going to solve for x2 in these equations to make them look like y equals mx plus b. So if I solve the first equation for x2, it would look like that, right? So subtract the x1, divide by -2, and you would get this. On this one, if you added x1, then divided by 3, you would get this. And so this now looks like y equals mx plus b, right? x2 is kind of like the y, x1 is the x. Those are the slopes, the 1/2 and 1/3. Those are the y-intercepts. And so we can graph those. They're 2 different lines. We can just go ahead and graph them on an xy axis. I do have my ruler here, so I'm going to go ahead and draw a quick xy axis. And as I mentioned, these are the y-intercepts, right? So let's see. One of them, I'll do the second one first. The second one has a y-intercept of 1 and a slope of 1/3. So up 1 over 3 would put us right here. And so the second line looks like this. Now, of course, I'm doing this by hand, so hopefully it works out nicely. I'm trying to use rulers to make sure it works, but we'll see. The second equation has a y-intercept of 1/2, so we'd put the y-intercept of 1/2, and then it has a slope of 1/2. So up 1 over 2 might be right there. Is that right? It didn't quite work out the way I'd like it to. Did I? Yeah, it's just not working out very good because I didn't draw this very well, unfortunately. But up 1 over 2 could look something like this. I'm going to try to fudge it a little bit so that it works out a little bit better. And so if we graph the second line, it should look like that. So, ignore the way I kind of fudged that a little bit. But the point is, the intersection point, the point where they intersect, is a place that's on both lines, right? It's the only place that's on both lines. And so that intersection point, which happens to be the point 3, 2, right? x1 equals 3, x2 equals 2, is a place that's on both lines. And so that's a point, right? That's an x1 comma x2 point that satisfies both equations. And so that's the solution, right? If we want to think about it, remember, we're trying to think about a solution that satisfies both equations at the same time. So that means it needs to be on both lines at the same time, which means it's got to be the intersection point. And we can check that, right? We can check pretty easily to see whether or not it satisfies both equations. Because if we plug in 3, 2 into both of these equations, it should satisfy both constants, right? So in the first equation, it would look like 3 minus 2 times 2. That would be 3 minus 4, which is -1. And that's what this one was. So that one worked. And the second one, if we plugged in the second one, it would be -3 plus 3 times 2. So -3 plus 6 is 3. And that's what we thought we got in the second one. So check. So 3, 2 is in fact a place on both lines, and so therefore it's a solution to the system. Okay, we're going to come back and sort of characterize that idea. Well, let's just go ahead and write it down actually now. The thing I'd like to point out here is that we get just one solution, right? It intersected at just one point, and so there's only one solution. In other words, the solution is unique. My pen is running out of ink here. I do have another one right here though, great. So that's something that can happen, is there's only one solution. In other words, there's only one intersection. And so we got a unique solution. So sometimes you might have a unique solution. Let's go on to one of the other possibilities. So we graphed the first one. Let's go down to the bottom left corner here, and we'll do one of the others for this one here. So on that one, I'm going to do back substitution on this one. So the first one we graphed. I should have been more clear about that. So we did number 3 in the first one, we graphed. In the second one here, we're going to do number 1, which is we're going to solve for one variable and then plug it into the other one. So let's solve for x1 in this one. In other words, let's get x1 by itself in either one of the equations. I'm going to just add 2x2 to the other side here to get x1 by itself in the first equation. And it would look like that, right? And so we have an expression for x1, and then we can take that expression for x1 and plug it into equation 2. Right, so I'm going to take this expression and put it into the x1 in the second one. So that would look like this. Right, so just imagine I took out this x1 and then I put in that expression for it, and it became this, right? And notice the nice thing about that is this new expression only has x2 in it. And so since it only has x2, we can solve for x2. So let's go ahead and do that. So we distribute the negative 1 through here, and we get minus 2x2 plus 1 plus 2x2 equals 3. Oh, but look what happened. Minus 2x2 plus 2x2, those things cancel, and we get 1 equals 3. Huh? That's kind of weird. What do you think happened there? Well, we ended up with something that doesn't make sense. 1 equal 3. That's just not true. And so that's telling us we have no solution to this equation. This system, I should say. Take a second to think about why that would happen, and think back to the first one here, right? We got a solution on this line, a unique solution, because the two lines intersected at one spot. So what do you think it means if there's no solution? That means? While you think about that, I will just do a quick sketch of what these might look like. It's because these two lines are parallel, right? They have the same slope, right? They both have a slope of 2. And so they're never going to intersect, right? They have the same slope. That's what makes parallel lines. And so when you have parallel lines, you're not going to get an intersection point like we did here. And so that's what makes no solution on this one. We ended up with parallel lines. In other words, no intersection. Okay. So sometimes people get bogged down in like these processes. I just want to be clear about something. We're not going to solve systems by graphing in this course. We're not going to solve via back substitution. We're not going to solve via adding, subtracting. I'm just sort of reminding you of past ways to do it to illustrate things that could happen. And the things that could happen so far is you might have a unique solution or you might have no solution. Okay? In the third example, we'll solve this one by doing number 2 here. We're going to add or subtract multiples of one equation to cancel out a variable. And the thing I'm looking at here, so let me just be clear, we're going to add or subtract the equations to cancel out a variable. And I just noticed right off the bat that like we have plus or minus x1, we also have plus or minus x2. And so we could just add the equations together and the variables will cancel. And so I'm going to add them. Or actually subtracting would do the same thing. So maybe I shouldn't write that. If we add or subtract them, all the variables are going to cancel on the left, and we get 0. But notice what happens on the right. The 1's cancel as well, right? If we add 1 and minus 1, they also cancel. And so we get 0 equals 0. That's a true statement. 0 does equal 0. And so we don't get like a weird issue like the last one, right? 1 equals 3 was weird. That didn't make sense. 0 equals 0 is true. And so we do actually get solutions here. But the interesting thing is, this is just the same line written twice, right? So if you multiply the first equation by -1, you get the second equation. And so if we were going to graph this, if I sort of graph this line, this might be the first equation, right? And then the second equation might be the exact same line. And so if we're thinking about intersection points, like on the first one here, right? We had one intersection point which led to one solution. This has infinitely many intersection points, right? So these are the same line. These are the same lines. And so we have infinitely many intersection points. Right? In other words, every point that's on one line is also on the other line. And so that means that this particular case will have infinitely many solutions. And so those are the three things that could potentially happen. Right, we've illustrated the three things that could happen. We could have a unique solution like we saw in the first one. That would sort of imply one intersection point. We could have no solutions. That would imply no intersection points. Or we could have infinitely many solutions, which implies infinitely many intersection points. Now the key thing to sort of keep in mind here is these are the most simple equations that we could ever see, right? There's only two variables, there's only two equations. We're going to be looking at equations and systems that have lots of variables and lots of potential equations. And so they don't look like lines anymore. They might look like pieces of paper going through space, or even higher dimensional things that we can't picture. But the thing to keep in mind is one of these three things is always going to happen. One unique solution, no solutions, or infinitely many solutions. Right? We're going to see those repeatedly throughout the course. And chapter 1 is all about like characterizing how we know which one of those cases we're in. Okay. I'm going to jump to the next page here. Of course, you can always feel free to pause the video if I'm going too quick. Usually in class I can get visual cues about when people are finished writing and things. Online I don't have those cues, so you may have to occasionally pause the video and finish writing, or you could always go back and hear me say something a second time. Okay, so we just saw these three things. Right? A system of equations might either have no solutions, so that would be example 2 on the last page. It might have one solution, that was the first example, or it might have infinitely many solutions, that was the third example. But those are the only three possibilities. They really, really are. Now let's write down some vocab. We say a system has, if a system has no solution, we call it inconsistent. So if no solution exists, we say that the system is inconsistent. Okay, so that's a vocab word. It's a vocab word that's going to come up a lot. Right? It means inconsistent because it's like you're writing down a bunch of equations that you hope satisfy, there's some solution that satisfy all of them, but they don't, right? That's not consistent. If there is a solution, so if one or more solutions exist, we say the system is consistent. So consistent means there is at least one solution. These are just vocab words, but they're important vocab words. They're vocab words that I'm going to use all the time, and I really am going to just expect that when I say, oh, this is inconsistent, you know what I mean, right? I'm not going to say, it means there's no solution, right? You need to know that that means there's no solution. This example here, this is a project I had worked on with a recent Fitchburg State graduate. This person was a cross-country student or a cross-country runner. and they wanted to know where the flattest place to run in Fitchburg is. And so they created this network of roads around the college with the distances, these are elevation changes between them. And then they created this linear system, right? So this is some massive linear system. I know it might not look like a linear system because it's written in shorthand with summation, but this is like a big linear system that has as many as 17 variables in it, right? And they wanted to solve this linear system. It was a huge, huge system, created a giant matrix. There's no way that anyone can solve a linear system that looks like this using one of the methods on the last page, right? So you can't graph these things because they're higher dimensions, so you can't even like look for intersection points. There's so many variables and equations, adding and subtracting them to get rid of variables isn't going to be successful. Too many equations and variables to back substitute. So what I'm trying to point out here is, I did these baby examples on this page, on the last page, to sort of give you some ideas. But in reality, when you get to the real world and you start doing real math, those things don't work anymore. And so that's where linear algebra comes in. So the takeaway here is we need better methods than just graphing or substituting. And so that's what we're trying to learn about in linear algebra. And so that's where matrices come in. Okay, so this is going to be where we introduce what a matrix is and talk about how we solve systems using those matrices. So any linear system like the one written right here, like really complicated ones, or even really simple ones like on the last page, can be written in a matrix. Right, so we can record the information presented in linear systems in a matrix. Then we can often do some of the same things we did on the last page, but we do it in matrix form. And so it's much, much more organized, quicker, streamlined, and moreover, when we start using calculators or computers, it's really, really quick to do in matrices as well. So here's a linear system that we're going to be messing around with. You can see it's a system of 3 equations and 3 unknowns, right? x1, x2, x3, and there's 3 lines. Now, what we can do is we can turn this into a matrix. And so there's a couple different kinds of matrices that we might be seeing in this course. One of them is the coefficient matrix, and one of them is the augmented matrix. So the coefficient matrix is just the matrix that you get when you write down all the coefficients. So as a reminder, the coefficients are the numbers that are multiplying the variables. So like 2 is a coefficient in this one, 1 is a coefficient in front of x2, 1 is a coefficient in front of x3 in that one, right? And so let's write down the coefficient matrix right here. We literally just copy down the left-hand side of this without the variables or the pluses or anything, right? So it'd be like 2, 1, 1 is the first line. Those are the coefficients. 6, 2, 1 are the coefficients in the second. Minus 2, 2, 1 are the coefficients in the third. Right, so it's kind of like this is the x1 column, this is the x2 column, this is the x3 column, right? These are the coefficients for each variable. Also notice how when I wrote down the matrix, just a little tip when you're writing matrices, it's helpful to just kind of start the box part of the matrix, then write all the things you want to write, and then finish the box, right? Oftentimes if you try to write a box and then fit the letters into that box or the numbers in there, you run out of room or it gets kind of squeezed. So I would recommend sort of just starting the matrix, writing the numbers down, and then finish the box. Just sort of a tip. Okay, so that's the coefficient matrix. The other kind of matrix that we're going to talk about that we use more often than the coefficient matrix is the augmented matrix. And so the augmented matrix, like it says here, is the same as the coefficient matrix, but we include the constants to the right of the coefficients. Oftentimes we represent the equal sign with a vertical bar. So the augmented matrix is kind of like the entire system written in a matrix. And so it's going to be the coefficient matrix, but then we're also going to include the constants here on the right. And so the augmented matrix would look like this. Again, notice how I'm going to kind of start the matrix, write my numbers in here, and then I'll finish it when I finish writing them. So that's the coefficient part, but we're also going to include the constants. And sometimes people represent equal sign with a bar just to kind of separate the variables from the constants. Now that I have everything written, I go ahead and close the matrix off. And so this is the augmented matrix because it's like we have x1, x2, x3 column. The vertical line represents the equal sign, and then we have the constants on the right, just like we did in the intro section, right? We talk about variables on one side, constants on the other side. Very, very common to do. The other sort of piece of vocab that we need on this page are just how we refer to the size of matrices. So we reference the size of matrix by saying it's m by n. So the first number you write down, the m, is going to be the number of rows, and then the second number you write down, the n, is the number of columns. So this coefficient matrix, for example, has 3 rows and 3 columns, right? And so to be clear, the columns go up and down, right? And the rows go side to side. The way to remember that is if you think about like columns on a building, right? Like Greek columns or the columns that sort of hold up a porch or something, columns go up and down. That's how I usually remember it. And then rows go side to side. So anyway, there's 3 rows and 3 columns in this one. And so this one right here is a 3 by 3 matrix. Right? We'd also call that square because it has as many rows as it does columns. And then this one here has an extra column because we included the constant. And so this one would be 3 rows and 4 columns. Okay. So just to be kind of more clear about that, we do number of rows by number of columns. Okay. All right, the next 2 pages are how we actually then solve this system, right? So we usually think about it in terms of an augmented matrix, and then we mess around, we do algebra with that matrix to solve a system. And so that's what we're going to look at in the next page. Okay, so we're going to start off with a nice, easy system again, right? 2 equations, 2 unknowns. And what we're going to do is we write it in a matrix, and we do operations, okay? And so like it says at the top of the page, when you're doing algebra with equations or row operations with a matrix, the following things don't change the solution. So you are allowed to multiply an equation by a non-zero constant. That won't change anything. Right? You can multiply both sides of the equation by something and it doesn't change. You can switch rows, or you can replace a row with a multiple of one row added to the other row. That's one that gets used more often than not. And so we're going to solve this system using those ideas, and I'm going to do it in 2 ways. I'm going to write down the equation form. That'll be over on this column, this side of the page, and then we'll do the exact same thing in the matrix form. And what we'll see is the same operations be carried out in both cases, but the matrix form is just a nicer, easier, more organized way to do it. Okay, so the first thing I'm going to do is write down the equation. So I'm going to rewrite that system. Right? And I'm going to write the exact same equation, but in augmented matrix form. So the matrix version of that, like we learned on the last page, would look like this. Right? You basically just get rid of the variables, and the equal sign is now just a vertical line. It's just nice. You're just focusing on the numbers rather than the variables, right? Okay. I'm also going to sort of go through each one of these things and show what they mean. So let's multiply an equation by a non-zero constant. So A. Let's think about what we could multiply row 1 by that would be helpful, right? Eventually we want to try to cancel out a variable. And so it could be nice if the x2s, or the x1s for that matter, had the same coefficient. And so for an example of A, let's multiply row 1 by -2. And when we multiply row 1 by -2, we're going to be able to cancel stuff out. Right, so I'm going to multiply the first row by -2, and we get this. Now I didn't do anything to the second row, so I'm just going to rewrite the second row the exact same. And I'm going to do it in the matrix form as well. It's going to be the exact same thing, right? We're going to multiply row 1 by -2, and we'll get a similar looking thing. So take a second to make sure that that makes sense to you. We just multiplied the first row by -2. And I did that because I wanted to be able to cancel out, say, this x1, which we'll do in just a second. But before we do that, let me just show you how we can interchange two rows. So interchanging two rows just literally means like flipping the equations, right? So we could flip the rows around and nothing changes. It's just like writing the equations in a different order, right? That doesn't matter. But let's just be clear. Example of B. Let's switch the rows. And when we switch the rows, it would be the exact same thing. The rows would just be in the opposite spots, right? So it would look like this. Right, just switch the rows, no big deal. And if we did it in the matrix form, we'd get a similar looking thing. Right, so those are examples of the first two things. We're allowed to multiply by a non-zero number, and we are allowed to switch the rows if we want to. Now, as I mentioned, the part C, replacing one row with a multiple of another added to it, that's what we usually end up doing to try to solve these things. And so the whole reason, as I mentioned, we multiply by -2 is because if I add the two equations together here, or if I add these two rows together, right, these two x1s are going to cancel, which we know is helpful from the intro section. And in other words, these two things are going to cancel. So for an example of C, we're going to multiply row 1 by 1. In other words, we're not going to change row 1. And then we're going to add it to row 2. And we're going to keep row 1 the same. Right, so I'm just going to add row 1 to row 2 to cancel out the x1. And when we do that, it looks like this, right? So I'm just going to add this number to that. I'm going to add this number to that. I'm going to add this number to that. And the same thing in the matrix. So the first row stays the same. The second row gets row 1 added to it. So we'd get 0x1, 4x2, and then -6 plus -4 is -10. And we would get the same looking thing in the matrix form, but with just the coefficients, right? Now, what we'll see is we can now solve this. Anytime you end up with basically one variable in a row, right? So this is just x2 in that row, just like here. You can now solve for x2. And so we can then rewrite as a system, right? So once we have a matrix that looks like this, we can rewrite it as a system and solve for x1 and x2. So when I rewrite this as a system, it looks like this. Right? It's really easy to get x2 by itself here. You just need to divide by 4, and then you have a solution for x2. And then when you have a solution for x2, you can plug it into the other equation to get a solution for x1, just like we did before. And so I'm going to solve for x2 here. Right? So this is our new system. I'm going to take the second equation, divide by 4 to get an answer for x2. So -10 over 4, or -5 halves. That's our x2 value, our x2 solution. And then you just plug it into an equation to get the other one. right? So we plug 5/2 into equation 1, and we would get an answer. So 4x1 plus 2 times minus 5/2 equals -4. The 2's cancel, and we get 4x1 plus -5 equals -4. Add the 5, divide by 4, you get an answer for x1. So in other words, our solution, our x1 comma x2 solution, our ordered pair in this case, is 1/4 comma minus 5/2. So we got a unique solution on this one. So if we graph these lines, they'd intersect in one spot. Now, do notice that, again, this is as easy as a problem gets. If you just have two equations with two unknowns, there's lots of easy ways to solve it. I'm just starting off with a nice, easy one so we can see how it works in matrix form. And the point here is sort of, we kind of know how to do things with equations, and I'm sort of trying to show you what it looks like when we don't do equations and we just do the matrix version, because we just want to be focusing on matrices in this class. We don't want to be messing around with some of the primitive solutions that we've seen in past sections. Okay. I'm going to finish this section with a more complicated example. And usually when I do this in person, I have people get together and team up and try to solve the next one in a team, and then we do it together. So I would strongly suggest you do that. Again, this is the kind of stuff that helps you learn, right? Just watching me do it over and over again is not going to help you learn how to do it. You've got to do it yourself at some point, right? And so I would strongly recommend that at this point in time, you try it. You don't have to, but I really, really strongly recommend you do. This is a more complicated system, and I'll help you get it set up. But once it's set up, I would suggest you pause the video and try it. So in the following, we're going to do the same kind of thing. We're going to do algebraic steps with just a matrix to solve this system. And so let's start by writing it as a matrix, right? So that would be the first kind of thing that I would suggest you pause and see if you can do. Can you write this as an augmented matrix? Right, so coefficients on one side, constants on the other. So I will go ahead and do that. Hopefully you have paused the video and tried that. So when you do that, it looks like this. And notice I'm writing in zeros in the spot where there are no variables, right? So if, for example, in the first equation, there's no x3 variable, and so I put a 0 in the x3 spot. Right? There's no x1 variable in that one, so there's a 0 in that spot. That's important because, as a reminder, we want all the x1 coefficients in the first column, the x2s and the x3s in their respective columns, right? And so these are obviously the constants on the right. Now, as you hopefully pause the video and try to solve this, let me just sort of try to reiterate what your goal is. And we're going to flesh out the details of this process in the next couple sections. We're really just introducing the idea right now, and then in the next couple sections we're going to make it more detailed. But the goal is we want to reduce this matrix by adding and subtracting multiples of rows so that the last row has only one term in it, right? Just like on the last page, right? We got down to the last row having only one term, and that let us solve for the x2 variable. But since there's 3 equations in this one, we want the last row to have one term. We want the second row to have at most 2 terms. If you can get less, that's great. And then it doesn't really matter what's in the first row, because once you have those 2 rows like that, you can solve for the first row. In other words, if we kind of think about what we want the matrix to end up looking like, we're going to get the solutions on the right side, but we want 0, 0, some number in the last row. Then we want 0, some number in the second row, and then it doesn't really matter what's in the top row. Okay, and so when I write that down, when I write number, that can be any number, even 0. It's okay if those number spots are zeros. The important thing is that this happens. We get zeros in those spots. This is really what we're gunning for. We're trying to get those to be zeros, right? So in other words, we're trying to get this part to be 0. We want all zeros there, and we already have 1, which is good. But we want to make the other 2 0, so that'll look like this. Then you can solve for x3. You plug that into here, solve for x2. You plug those into there, solve for x1. That's sort of the general idea. So again, I would strongly recommend you give this a try. There are different routes to get to the right answer. When I did this, it took me, and when I do it in a second, I'll do 4 steps. So you should think about, in about 4 steps, you should be able to get this matrix to look like this, right? You get zeros down there. So again, please pause and give that a try. When you're done, unpause, and I'm going to start going over it right now. Okay, so when I'm looking at this matrix, right, I want zeros in those spots, and I already have 1, so that's good. Right? You always want to get a 0 down there first. Now I'm also seeing that I want this to be a 0, and if I add that 1 to this one, it would make it a 0. But I can't just like add that 1 to that one. You have to add rows, right? You have to follow the things on the last page. You have to replace one row with a multiple of another added to it. So what I'm going to do is I'm going to eliminate the x1 coefficient in row 2 by adding row 1 to row 2. And the way we note that, this is an important sort of step here, is I'm going to note that as I'm going to take row 2 and I'm going to add to it row 1. And we write a tilde. Instead of equal signs, you know, oftentimes in math you write like this equals this equals this. We don't write equal signs. We say is equivalent to. And then we write down the new matrix that happened. And I just want to reiterate this again. You write down the row you're changing first. So I'm going to change row 2. What am I doing to it? I'm going to add to it row 1. Right? This is really important for both grading purposes because I want to see the steps that you're doing, and it's hard for me to guess what steps you did without you writing that down. But it's really important for you because if you mess something up, which these are very easy to mess up, you want to be able to go back and double check what you did, and you want to have a good notation about what you did. Right? So this is telling me, okay, I'm going to take row 2, I'm going to add to it row 1. Right? So I'm going to do like 1 plus -1. I'm going to take this and add -3. I'm going to take this and add 0. I'm going to take this and add 5. Right? And when you do that, it becomes this. So the first row doesn't change. We're changing the second row, so I'm going to rewrite the first and the third row. Those don't change. Right, we're not changing rows 1 and 3, we're changing row 2. And so when I do 1 plus -1, we get 0. That was the goal. 1 plus -3 is -2. 5 plus 0 is 5. 2 plus 5 is 7. And so we've got a couple zeros here, which is what we want, right? We have those 2 zeros, those were our goal. We just want to think about how to make this one a 0. Let's just sort of pause there for a second, let you think about that. Okay, so we have these 2 zeros, that's good. We want to make this one a 0, right? We want to make that 1 a 0. And so if this was a 2, we could use that -2 to cancel it. So on my next step, I'm going to do row 3 times 2. So I'm taking row 3, multiplying it by 2. Right? And so these are both going to become 2's. This is going to stay 0. So rows 1 and 2 are not going to change. But row 3 is multiplied by 2. And again, the reason we wanted to do that is because now I can add this -2 to that 2 to cancel that one out, and then we'll have it looking like the form we wanted it to be. And so again, you write down the row you're going to change, and then you write down how you're changing it. So I'm going to take row 3, and I'm going to add to it row 2. right? And so the way we write that here is take row 3 and add to it row 2. All right, if you switch those two things, if you did R2 plus R3, that's telling me you're taking row 2 and then adding row 3. All right, so it's very important. You write down the row you're changing and then how you're changing it. Excuse me. So I'm changing row 3, so that means rows 1 and 2 are not going to change. So I'm just going to rewrite those without changing them. But then I'm going to change row 3. So I'm going to do 0 plus 0 stays 0. 2 plus negative 2 becomes 0. 2 plus 5 becomes 7. 0 plus 7 becomes 7. And now we have the thing we wanted. We've got these to be zeros, which was our goal originally. We can easily solve for the x3 variable, and then we can plug that into the second equation, get x2. We can plug both of those in the first equation and get x1. Before we do that, I'm going to make it maybe a little bit easier by making this a 1 down here. So I'm going to take row 3 and I'm going to multiply it by 1/7. Just to put a 1 in that spot, just to make it a little bit easier. And we have a word for that. It's getting towards what's called echelon form, which we'll see in a future section when we start to really define some of these things. Right, so just multiplying row 3 by 1/7 just changes those 7s into 1s. Again, we still have this nice thing where we have the situation we wanted. And then when we write down the equations, slide this up, excuse me. When we write down the equations to solve, they just fall right out. Right, so I'm going to write down all 3 equations. Here's the system as it's up there. x1 minus 3x2 equals 5. The second row says minus 2x2 plus 5x3 equals 7. The third equation just says x3 equals 1. And so that's the solution, right? The x3 variable is 1. That was the whole point of getting 0, 0, not 0, is because we just get the x3 variable solved right off the bat. And then you can take that, plug it into this x3 to get x2, right? So we're going to take this, we're going to plug into equation 2 to get this. So when we solve that, right, just subtract, divide by 2, we get x2 is negative 1. So that's the x2 value. And then we can take either one of those, whatever is needed to plug into equation 1 to get the other variable. So when I plug that into equation 1, we get x1 minus 3 times negative 1 equals 5. We easily get that x1 is 2. And so we get a unique solution. Right, our solution in this case is x1, x2, x3 is the pair, or the point 2 minus 1, 1. It's a unique solution. We only get one of them, and that's what it is. Right, so the takeaway in this section is like how we take, so there's some vocab early on, right? There's some vocab about just reminding us about how to solve systems, some vocab about different types of matrices, right? Translating from a system to a matrix. Oh, right, vocab about inconsistent and consistent. And then we just solved a couple of very simple equations, like a very, very simple one, sort of paralleling the system with the matrix form. And then a more complicated one that I do hope you tried to give yourself a chance at it, where it was a three equation system. We did the operations we were allowed to do, and we ended up with a unique solution. As we move into the next section, we're going to formalize this process. You can see the next section is called row reduction and echelon form. And so that's going to formalize this idea, and we'll move forward in talking about how we solve more complicated equations.